We call area traffic control, and which I normally call it into two. One is a responsive one and an adaptive one. It's true that vehicle actuator is also in some sense adaptive or responsive. We'll explain those concepts now. Fixed time control, as you all know, based on typical pattern of driving, we divide the day into number of periods, we'll say AM, morning peak, noon, evening peak, etc. And where we assume the traffic flow is known, and based on that, we try to find out what is the cycle length and what is the green time, so on, etc. Which is pretty constant. It's very simple in its implementation, because you don't need any major hardware, etc. By the way, when we think about traffic signal control, there are various ways that we can do signal control. Many of them are predominantly guided by the geometric considerations. But traffic signal control is basically what that stands out of all the other type of signal control, where it has the potential to adapt to the fluctuations in traffic. All the other type of controls, for example, roundabouts or channelizations, etc., they are pretty static. Irrespective of what is the current traffic flow, the traffic control is changing. But traffic signal control has that great potential that it can change with the signal control, but change with the traffic flow. At the same time, it is also dangerous. It's like a sharp weapon that you have. It's easy to cut. At the same time, if you don't use carefully, you can cut ourselves. In a similar way, it is so flexible that it can change with the fluctuations of traffic. At the same time, a carelessly designed signal can also have greater impact. And I also would say that this is one area where people perceive a poor design very easily. For example, somebody designs a roundabout in a wrongly. Hardly anybody will find any fault with the roundabout. Okay? They think it's a part of the thing. But when a signal fails, then it is something that is easily noticed by everybody. For example, there is traffic on all the three legs. On one leg there is no vehicle, but there is green time. Everybody will say, okay, this is a very bad design. Or suppose there is very less time is given in one particular approach, and more demand is there on that one. The queue builds up and blocks the preceding junctions. So these all have more direct impact as far as the road user is concerned. So on one side there is a great potential to fluctuate with the traffic conditions, but on the other side it also has a challenge. So now, so this is pretty straightforward, the fixed time control. But then we have the coordinated control. On paper it looks very nice. What if we adjust the starting of the green or maybe ending of the green in such a way that when the vehicles come from one junction, when it reaches the next junction, it also will get a green time. So it looks very nice. All this green wave, what we call as, will get continuous green, so that vehicle can move, and this works nicely, provided so many conditions like assuming some constant speed for these vehicles, and all these vehicles are moving like a platoon, and etc. etc. There's no much side friction, there's no much side tractions, etc. It has a great potential that way, especially we have directional traffic. Let's say morning there is one traffic in one direction, evening there can be opposite direction. So there is more demand in one direction in certain time. So this can be taken care of that one. There are so many benefits of coordination is there. But in reality, it also has major challenges, because it assumes so many things, like even though we can say that there is green band in one direction, getting green band on the other direction is also a great challenge. Then comes the vehicle actuation. Vehicle actuation. So it works based on a simple concept that when there are some vehicle sensors are there, and especially this diagram is assuming that there is a stop line sensor is there, which will try to find out whether a vehicle is there or not, and then if there are vehicles are there, Okay, we need to say that okay, green time is there, and this one there is simple assumption that okay, we start with a initial green time, some minimum green time that is given, and then the vehicle is there. Okay, the green time can be extended till some maximum is reached, or if the demand is reduced, we can curtail the signal by this time. So this is also can be in two ways. It can be reactive or it can be truly adaptive. When it means reactive, you can always think about like a policeman standing at a junction and then trying to control the vehicle. Now this policeman can act in two different ways actually. One, he looks only at one junction, okay, and then the vehicle is or the queue is clear, then he turns to the next junction and then try to clear that one. Okay, so that is one model. Okay, so when this policeman is looking in one direction, he's blind to what is happening on all the three other directions. Okay, that's one model. But suppose if the policeman is looking at here, even though vehicles are coming, but he also looks the other three junctions, and if there is a big queue is building up on the other junctions, then even though there is a queue here, he curtails this green and then give green to other junctions. So which is what we call as a truly adaptive. Truly adaptive. The person also is like an adaptive, but it looks only at one junction, only one approach, and then he is blind to the other approaches. Okay, yeah. So the same thing what I said, putting in a different way. The fixed time control. This diagram nicely illustrates that okay, depending upon the time of day, there are different signal programs are there. Okay, that's typically fixed time control works. It does not communicate with what is really happening in the field. So morning one program, afternoon one programs, etc. The area traffic control also, or adaptive control also, as I said, can be responsive in the sense that okay, certain pattern of demand, one signal plan, certain other pattern of demand, another pattern. So the controller is basically doing is looking at the field and find out okay which pattern that is happening, and corresponding to that one there is a signal program that is happening. Okay, which is what I think most of the what they call as adaptive traffic controls are actually working. I would say they are not actually adaptive, but what they do is based on certain assumed pattern, the timing is computed, and then pick up from, so it has a library of plans out there, and they pick up from the current traffic condition which plan may be best suited and picks up that one and executed that one. But a truly adaptive one do not have any a priori plans are there. Okay, based on the traffic situation, it collects and find out what is an optimal plan, and that will be implemented for that cycle. In the next cycle, or maybe after the next 3 or 4 cycles, the plan is changed depending upon the demand is changing. Okay, now this is in a nutshell, I would say the taxonomy of signal control, isolated control, vehicle actuated control, coordinated control, area traffic control. This vehicle actuation and area traffic control can work either as a responsive or as an adaptive. Now coming to two popular philosophies of area traffic control, which we all know about, SCOOT and SCAT, which are the two major adaptive controls available. Okay, even though they claim adaptive, I would not say that they are truly adaptive. They are, I would say, mostly a responsive thing. SCOOT, the why I am saying this only to these is not because these are the two only solutions, but they have two different philosophies of adaptive control. Okay, so therefore I am highlighting on this one. My interest is not on these two solutions. My interest is on two different philosophies of area traffic control. Okay. Now, to simplify, assuming that there is 4 junctions are there, the one philosophy works based on distributed system. Okay. And another philosophy works on a centralized system. Okay. Now think about this centralized system, which is the SCOOT system. So what it does is, So suppose for controlling this junction, the sensors are away from that junction. And then what these sensors will do, they will collect the traffic information and give it to what we call as a central controller. And what the central controller will do, they will try to predict when these vehicles will come at the junction. Similarly, junction 2, junction 3, junction 4. Okay. So many sensors are there, they are far away from the junctions, and central controller will predict when these vehicles will come at each junction. And then what it does is, it computes an optimal timing and send it to each of the signal heads. So this is what I was telling. The characteristic working philosophy is an upstream detection, that is far from the junction, and the data goes to the signal controller. Optimal timing is computed and sent back to individual junctions. So it's nice. I would say it's a implemented in many places, but it has challenges in our country because the communication overheads, the amount of data that need to be communicated to central controller. So that means there will be a sensor for each lane, each approach, each junction, multiplied by what many number of junctions are there. All this data has to come to the central controller, has to process all this data. So there's a huge overhead is there. Another challenge is the progression prediction. I said it's easy to say that, okay, we get upstream information is there, traffic information is there. To predict when it comes to the downstream junction is a challenge, especially in our traffic where there is heterogeneity in speeds and class of vehicles, where platinum flow does not hardly exist. Okay. Then these calibration issues are there. Okay, these sensors, although it captures the traffic data, but we know that okay, it's not able to capture exactly all the vehicle composition. So the calibration issues are all there. So this is one good philosophy which is working in many places. And one of the difficulty is, now these systems are also implemented in our country in many cities, and but they don't work nicely. They don't work nicely because of these issues. Now this is one philosophy. Now the other philosophy is a distributed system, which I would say distributed stop-line detection. Earlier one was a centralized upstream detection. Now this is a distributed stop-line detection. Same for junctions, but here the sensors for that junction is kept at the stop line. Okay, and all these sensors will communicate to a local controller, and this local controller, depending upon the current traffic conditions, it works just like a vehicle actuator control, and to the local junction it tells what is the signal timing. Similarly for junction 2, junction 3, junction 4. Now where is the area traffic control is there? Now all these 4 junctions periodically communicate with the central controller. Earlier case, the communications were every 1/4 of a second or every second. But here, at the end of every cycle, maybe 1 minute or 2 minutes, in that interval, it communicates with the central controller. It communicates with very less information. What communicate? Okay, currently you have given me 30 seconds mean time, I used 26 seconds. Or my other approach, you have given me 40 seconds, I used all the 40 seconds. So this information is communicated to the central controller. So what the central controller will do is, based on that information, it try to capture, okay, the traffic is growing in one approach, or traffic is coming down in one approach. Depending upon that, mean time is increased or mean time is reduced. So that philosophy is downstream detection. Each local controller act like a vehicle actuator controller, isolated vehicle actuator controller, but communicate periodically to the central controller. Limitation is, yes, it is not an optimal system. What it does is, okay, it uses the present state, using the present state, and then trying to communicate the timing for the next interval. Whereas the earlier system, it predicts from earlier timing, and then for this cycle, it will be communicating, it will be commuting based on the current traffic information. But here, it is not an optimal because it is trying to take the present information and using that computing the timing for the future. Okay, however, if you actually compare these two, the centralized system is a nice concept. an optimal concept is a model-based system. However, a lot of practical issues are there. Whereas the distributed system, we not say that there is no sound models are there, but it works more like a heuristic, and these issues are there. So I just wanted to say that these are the two philosophies. Any adaptive traffic control systems can be generally put into one of these categories. With this, we try to look at some research that we can do in this perspective, which is actually done in that one. Okay. Now, as I said, the traditional vehicle actual controller is like a policeman looking at one direction. He is blind to what is happening on all the other approaches. Now, what if we can mimic a policeman who try to, while he is trying to control direction one approach, he is also aware about what is happening on the other three approaches. Okay, how can we do that? A very, very simple thing. By traditional vehicle actual controller, this maximum green time is fixed. Although it is vehicle actuation, the maximum green time is fixed anyway. That means the policeman is blind to, his eyes is fixed only on one approach, he is blind to all the other approaches. Now what if we make it this also dynamic? Okay. There are various ways to do that one. One of the one is, okay, we have this adaptive learning things. Okay. By looking at how the traffic is picking up, we can learn by a system and then try to adjust this maximum green time. So by adjusting a traditional vehicle actual controller, by adjusting only the maximum green time, it can work like a truly adaptive system. We can use, instead of machine learning, we can also use heuristics also for attaining this one. But this is what is shown here, one example. Now let us say some results actually. Now look at this graph that is shown there. It is the demand that is coming on a junction from two directions. Okay, I'm not ignore the cross directions, which is assuming to be small side roads. But imagine there is a major corridor and traffic is moving. Let's say the morning direction, it goes and picks up and then goes down. Opposite direction, you have a completely different direction. So suppose, and again there is micro fluctuations are there within an hour, within 15 minutes also traffic fluctuates. So that's also seen. So there is a larger pattern, the traffic is increasing and decreasing, and there is also a micro pattern where within a short interval also traffic fluctuates. Now this is what happens in a typical vehicle actual control. Depending upon what is the maximum green time, see when the traffic is less, the volume is less, it's adaptive to the traffic condition. But this traffic is not able to capture because this is constrained by what we call as the maximum green time. Now what if you do the earlier, the proposed methodology which actually try to modify even the maximum green time. This is what it looks like. So this is the demand in one direction and this is the corresponding green time. So this is the demand in the opposite direction and this is the timing, the green timing in the opposite direction. So it is able to capture the major trends, at the same time it is also somewhat able to capture the micro trends also, which is in a sense a good enough system. Okay, I will skip this, it's not very relevant in this for the interest of time. Okay. I'll take the next 10 minutes to tell some of the issues that emerging directions or some issues that need to be understood. Okay. The first one is adaptive traffic control evaluation. Okay. How do we evaluate a typical adaptive traffic control? Isolated fixed time controls can be evaluated by finding what is the minimum delay, etc. Now, can we use the same thing for area traffic control? Yes, we can use delay is definitely one parameter, but delay alone may not be able to speak about whether it is actually adaptive. So some of the issues are improvement in junction delay. Okay. Now the reason I am telling you, okay, now as I said, there are a lot of area traffic control systems are there in very, very different cities in our country, including Mumbai, Bangalore, Hyderabad, Delhi. I'm not sure about the city. Many cities, Indore I know that it is there. But issue is actually many of these systems are handled by traffic police who may not have much understanding on the traffic dynamics. So they can be easily fooled. Okay, and that is one of the reasons this is also not adapted in many cities. So what I'm trying to say is, one of these criteria to evaluate how an adaptive traffic control works is in addition to delay, etc., this proportion of vehicles arriving at the green time. Okay, so those of you might have studied about HCM on signal control. They divide the arrival time into 6. Okay, dense platoon coming at the beginning of the green time on one extreme. The other extreme is dense platoon coming at the beginning of the red. And then an ideal situation, the middle situation is vehicle randomly arriving. Okay. Now for an adaptive control, one of the things to evaluate whether that is working nicely is whether there is a platoon, and if that platoon is coming at the beginning of the green. If the platoon is coming at the beginning of the green, that means all those vehicles will be getting cleared during the green time. So that is one. This is one probably the most important parameter with which that we can evaluate and a coordination, and especially adaptive control works. Then of course we can see on a little more micro level, looking at the travel time, vehicle trajectory, whether this is working nicely. So just keep this point in mind. Now some of the emerging areas, some of the needs that is there actually. One hard problem in coordinated control is, it's very easy to, I would say, relatively easy to coordinate on one direction. Now what if you want to coordinate on both directions? Of course, in some situations you may not have a solution available, especially if there are a number of tensions are there. But if the number of tensions are small, in some situations, how can we do coordinate on both directions? Okay, that is one area which now some research is happening, because coordination earlier assumes there is a clear directional traffic. But in many situations that may not be true. There can be vehicles that is moving almost same in both directions. Okay. Now how do we coordinate in such situations? Okay, that's one. Okay, now we all know that there is a lot of interest is happening on the digital twin. So how can we actually do that? Of course, one area is now the traffic control can be coupled with some microsimulation like BISIM or SUMO or something like that. In addition to that one, if you want to have a two-way digital twin, then what is happening in the signal control also should come back to the simulation or the signal control part. Then there will be a completely two-way digital twin. So this is another area that is emerging. Now, one interesting aspect in the signal control is dynamic programming. So how can we keep this top line information as well as it is truly